Okay. So the last talk of this session and the last talk of this conference is about links between quantum distinguishers based on Feynman's algorithm and truncated differentials. The work by Zijun Shan, Shan Wang, Bo Yu, Bin Sun, Chasa Zhan, Shan Yong Zing, Shan Shen, and Yan Li. And the talk will be given by Xiao Yu Wan.
Yes. Thank you. Hello, everyone. Good morning. I'm Xiao Yuan from Hubei University of China. The title of my presentation is the links between quantum distinguishers based on Siemens algorithm and truncated differentials. This is a joint work with Zijun Xiang, Bo Yu, and Bin Sun et al. My presentation is divided into 5 parts. Firstly, we will briefly introduce the background of our work, and then in the second and the third parts, we will discuss the construction theory of our methods. Finally, we conclude our work. With the rapid development of the physicals and computing, the quantum computing has attracted widespread attention, affects the security of cryptography. Um, in public key cryptography, the short algorithm can factor the large intelligence and serve discrete logarithms in polarity time, and in symmetrical cryptography, the graph algorithm can in polarity time. The Siemens algorithm has its advantage in attacking symmetrical ciphers. The Siemens algorithm can be used to solve the same problem. When the function is a function this function, and we will get a random output vector is organized to S. Then we can solve the linear equations in polarity time and to recover the S. So based on this theory, we can use the Siemens algorithm to construct some distinguishers. However, in the most case, the Siemens promise is difficult to satisfy. So, Captain Ito and Ito studied the intention of the Siemens algorithm, and finally, the constructing the distinguishers based on Siemens algorithm can be transformed into designing practical functions. If a function is a practical function, we can try to from the differential view to observe it. It means that the function has a differential s to 0 with probably 1. And we can get the number 1. However, it is we can consider the more consider a general case. This form. In addition, we can naturally extend this case for the more general case. For example, truncated difference. In this time, we need the matrix to help us construct a practical function. So we introduce the definition of the difference and elimination matrix to help us with construct a practical function. So we can prove the theory one if 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 a black cipher E has a truncated differential with property 1, there I2, there O, and there O has a difference and elimination matrix. Then we can construct a practical function just like this form. And we give the ordered one to evaluate the difference and elimination matrix to for any set. So we also call the hermetication function as constructed in theory one, a type 1 paradification, just as these fingers shows directly. For the facial structure, if we try to use type 1 paradification to construct a distinguisher, but we can get only 2 round distinguishers. However, as we all know, the 3-round distinguisher of the facial structure exists. It is given by the Kawakato and Mori. And the practical function of this distinguisher is just like this. One practical function to construct new functions and finally extending the quantity distinguishers. We can prove the theory 2. If a black cipher E has a R2 round provided 1 truncated differential, the I2, the O, and the L has a difference and elimination matrix. Moreover, one of the inputs belong to a Fayet space, and the R1 round different transition there to there I has a priority of 1. Then we can construct a new practical function, just like these forms. These figures show the theorem 2, and we can directly look in this practical function from the differential view. And we also call the practical function as constructed in theorem 2, a type 2 practical function. And this is a figure we can directly understand this type practical functions. For example, we can, with considering the facial structure, the practical of the 3-round distinguishers is a type 2 practical functions. And, and we in order to show our methods, we applied this method to ciphers. Some we first apply it to the air block and the Simon ciphers. Regarding the air block, we can find a 7-round truncated differentials with property 1, and we extend it 1 round. Finally, an 8-round distinguishers of air block can be found. For the Siemens ciphers, we take Siemens 32 as an example. We can find a 6-round truncated differentials with property 1, and we can extend it. And finally, a 7-round distinguisher of Siemens 32 can be found. Especially the Siemens ciphers are facial FK structures. This is very special, So we can extend it background and with can extend it background and first round by 1 round. So 9-round distinguishers of Siemens 32 can be constructed. For other Siemens variants, we can also do this. We can also construct longer distinguishers. These results are in this table. We can see this. We can find we can find longer distinguishers. In addition to symmetrical ciphers, we can apply our method to the structures. We consider the united structure because it covering many graphic structures. The composition of the each round of the united structure can be shown in this figure. Linear transformation and sum, and the round function, and linear animation, and some array branch, and finally is the branching permutation. And we also did some important parameters. And here are many special instances of the United States, just like such as phase law structure, the massive structure, and type 1 generalized phase structure, and SM4 and Mars structures. For the United structure, we can derive some important difference impressions. When the input difference is the delta 0, then after R round, the output difference is the special forms. Based on this impression, we can prove some conclusion. For a united structure, if this rank is less than ND, then we can prove there always exists any round truncated differentials with probably 1. And this means that this case, the united structure is not self. We can use the Siemens algorithm to break it. And then we can further prove that there always exists an R1 plus R2 round probably 1 truncated differentials. Need to rank in court and D. This means we can construct a R1 plus R2 round distinguishers for this united structure. For example, we can take the SM4 structure as an example. We can get the R1 in core 3, and we can compute the R2 in core 3, and finally we can find a 6-round truncated differential with probably 1, just like these fingers presence. We also consider the boundary in the probably 1 truncated differential. We can prove that there doesn't exist an R round probably 1 truncated differential when the round R is more than R1 plus R2. This means we can just construct the R1 plus R2 distinguishers for the united structure. In order to construct longer distinguishers, we also consider the extension of probably 1 truncated differentials. For I equals 1, 2, etc. And this case, we can extend plus R2 plus 1 round distinguishers can be constructed And for the second case is the A pi B equals I and A pi B equals 0 matrix for I equals 2, 3, etc. This case, we can extend it to R1 plus R2 round quantity distinguishers. We can take some examples. For the first case, the SM4 structure, we can found 6 round truncated difference, and we can extend it. For the second case, we can take the 4-branch type 1 generalized phase structure. We can for this structure we can construct the 6 round truncated difference with probability 1. And we can extend it 3 round, and finally a 9 round distinguishers can be constructed. Finally, we conclusion our work. Firstly, we show how to construct distinguishers based on Siemens reason by differentials. We reveals the links between quantity distinguishers based on Siemens reason and truncated differentials. And we define 2 types of practical functions. So we give the general approaches to constructing such distinguishers from the truncated differentials. And these methods cover most existing studies. And we also apply our method to air block and Siemens ciphers. We can find the longest distinguishers, the dedicated distinguisher. For air block, we can find 4 rounds longer than the previous generic result. And for the Siemens ciphers, Siemens family ciphers, we can find longer distinguishers also. And finally, we apply our methods to the united structures. One truncated difference. We consider 2 cases. The first case can cover the phase SM4-like and Mars-like, and the second case can cover the type 1 general phase structure. We can extend it D minus 1 round. That's all. Thank you.
Thank you very much. So you have questions from the audience?